My talk is going to be broken into two different parts because I originally thought that I was going to talk mostly to graduate students, so I prepared a more technical class sort of talk. But given what we heard today, I changed that, and so the other half of the talk would be more about ethical issues in robotics, which I also very much care about. So really two different things. I'll start first with really the title of the talk. So for quite some time, some of you may be aware of the work that we did in my lab, so to try to demonstrate how we can really have robots go beyond humans and be able to move super quickly and compute things extremely rapidly, such as being able to catch objects flying. And this required, obviously, to have machine learning, because when you want to catch an object like this one, which is half filled with liquid, it's extremely difficult to predict how the liquid is going to move when you're throwing the bottle through the air. There is no exact mathematical model for this. So, so this is how we really bridge machine learning with control, observing that when you have an object like this one, which is flying with a highly nonlinear trajectory, then you need to be able to estimate the object's flights, and so for these data-driven methods are ideal. But when it comes to actually catching the object, you cannot just go with machine learning. You need to have guarantees that guarantee that you will actually converge to the point and that you will be stable. That means that asymptotically you will get there. And you need to do that extremely rapidly. So it cannot be done with tons of data. It cannot be done with a very large model. Preferably, you want to have something which is called analytical or closed form in a way that you can compute it in real time in milliseconds. So this is, as I said, is a combination between machine learning for modeling the highly nonlinear dynamics and the control method for controlling for the convergence and stability, which allows you to then react once you have convergence stability. If you have inaccuracy in your prediction, then you re-estimate it online, and then you restabilize by placing the origin on the system. Now, I'd like to mention, and this is really meant for the junior researcher, that if you take just machine learning out of the box, support vector machine, neural networks, any of those support vector regression model, it will not do the job. Why? Because those models will drift. They will do very accurate estimates of the nonlinear dynamics. So for instance, if you estimate a vector field, as we've seen this morning, which is a vector field to bring your robot to the target, if there is any small inaccuracy in the modeling of the speed is not exactly zero, then the robot will continue moving. And this is true of autonomous cars that are being driven currently with regression technique predicting the velocity of the car. You have to have guarantees of stability and stopping eventually, really, and stopping means equal zero. So this is very well known in physics. This is known as systems for which you can guarantee the convergence to a fixed point. Fixed points means that you have your derivative is vanishing. And to prove that a system is converging, there are various ways to do that. If it's a linear system, it's trivial. If it's a nonlinear system, it's more difficult. And usually one will use an external observable function, which is known as a Lyapunov function. It's essentially an energy function, and you will prove that the energy of the system vanishes. That means you stop. Again, there is no motion. Now, in practice, when you learn any of those systems, you usually know neither the actual dynamics, that means this function, f, so what is the dynamics of your system, but you don't know the Lyapunov function, the stability and the energy. So one can try to learn it, and the very first work that we started doing in the lab was to see if you train a system and you present a couple of demonstrations. So you start off with just a handful of demonstrations. How can you then learn combining machine learning with control guarantees to ensure that you will learn a system that will have some stability property, including vanishing at this target? And the very first thing that we looked at was to use Gaussian mixture model, which is a density-based approach where you can build a sequence of Gauss function that will represent the system. You can generate an estimate of your velocity, and then you have a closed form solution. So here you have an analytical solution, and you can even derive, choosing a Lyapunov function, which can be a simple quadratic form that vanishes, and you can prove that it will stabilize. And you can even formulate this as a constraint-based optimization problem and prove that the learned system will be stable. And this is an example of the system you will get. You can also use the similar system to stabilize an external system that's been learned with support vector machine or neural networks or any other nonlinear regression technique, and then restabilize it afterwards by taking the gradient of the system. Now we've used this to train. One thing I haven't mentioned is how do we then train to machine learning to recognize the flying bottle, for instance, the flying racket. One can do that by estimating here from pure support vector regression, for instance, or neural networks, and then combine this with extended Kalman filter, and you will get a good estimate. And we showed multiple examples of how this could be done to catch a variety of systems with quite accuracy. And we also show that you can couple those systems, so those dynamical systems can be coupled easily in such a way that you can have two robotic arms that are jointly reaching for an object, which is very difficult to predict. Is another example that we picked. When you throw a flexible bar like this, again, you cannot have an explicit model of how the bar is going to fly. So what matters is that you ensure that your system can adapt to the flying motion. We also looked at multi-attractor systems, so not just converging at one attractor point, but being able to move around attracting point. And we started with the observation that if you wanted to have two dynamical systems with two different attractors, then you will have to partition the space. And going back to machine learning, support vector machine is a nice way to partition space. If you are familiar with this, it's an automatic partitioning of the space in two classes. But this is also implicitly a way of learning a Lyapunov function, because by construction, your partition is defined by a partition that is at a function which is equal to 0. And on the left-hand side, all the function is negative. So this is a Lyapunov function. But the traditional support vector machine will not guarantee that your Lyapunov function vanishes at the point where you would like it to vanish. So this was a second contribution that we did at the time, was to take again the support vector machine framework, take the classical one, where you take all the constraints, making sure that the points on both sides are classified, and then add other constraints that will force the system to follow the dynamics and stabilize at the attractor, and eventually show that this was still a convex optimization and you could solve that. So another example of combining machine learning with theoretical guarantees. And we showed example of doing this for catching in flight, for instance, an object like this, where there are two attractors. They live in joint space. When you want to catch the bottle at the rim or at the neck, you have to close the joints in different locations. So those are two different attractors in joint space, and you can do that in milliseconds. These were supervised learning problems with an exact partitioning of the space. And I went super fast on this because I like to spend just a little bit more time presenting another type of work that we've just done recently, which I'm fairly excited about. It's still relatively theoretical, but I hope you will allow me to just discuss this for a second. Machine learning is often used for supervised learning problems primarily those days, but I think we are overlooking unsupervised problems, and these form the majority of the problem that we really face today. In dynamical system, there are tons of examples of unsupervised problems. This is just one of the known dynamical systems, the Duffing dynamics. The Duffing dynamics has two attractors. Here it's in 2D, but you could also lift it in higher dimension. Has two attractors, and its particularity is that there are no clear partitioning of the space. In fact, there are points in space that are really almost collocated, infinitely small to one another, but if you slightly move to the right-hand side, then you will converge to a different attractor. And this is extremely important to detect those different variations, because this means also that if you want to characterize the stability of your system, you need to be able to know if you're following dynamic A or dynamic B. And the problem also in unsupervised learning for dynamical system is that usually you don't know neither the shape of the dynamics nor the number of dynamics that exist, and nor their attractors. So what we wanted to look at is how can we automatically learn now, extract from data points how many dynamics there are, which shape, basically what are the functions of all of those dynamics, and what are the attractors. So imagine that you're provided with a set of data points, and all what you have are data points x and x dot, whichever is the dimension of x. So position and velocity, so the derivative, which is sufficient to estimate a dynamical system. But these are unlabeled data points. So they are not only unlabeled, but they are unordered. So you don't know which one belongs to which dynamics. But each of those are just elements that you have sampled the space from. So what you can do is build a graph to connect those points. And this is going back to graph theory. And so we took some of the basic theorem that exists in graph theory and just apply them and push them just one step forward. So in graph theory, it's classical that you build a graph by looking at a similarity matrix. So you will say, if 2 points are adjacent, then the graph is connected. If they're not close to one another, then it's not connected. But the key thing is, what does it mean to be connected? So what we proposed was to use a velocity kernel, which will measure the locality. 2 points that are far, are deemed to not be close. Of course, if they're close, like an RBF kernel, then they're deemed to be close to one another. But as I mentioned, be careful, because with the different dynamics, 2 points that are close still leads you to different dynamics. So it's insufficient. So what you need to look at is the directionality and the continuity. And if you combine these two kernels, looking at both the directionality of the vector field and the 2 points close together, then you can build an actual way of discriminating between two dynamics. I'll give you an example here. If you use a traditional RBF kernel, which is only measuring for locality, when you have two dynamics like this one, two sample trajectory from the different dynamics, then you will connect them. And this is what we see when we look at the cross table, that these two regions will be collected, which is wrong. But if you use the velocity kernel, then you will be able to completely disconnect them. And actually, I was thinking it's too bad that Cyril is not here, but I'm going to talk to him, because this could be very useful for him to be able also to disambiguate the vector field that represents those petals, especially if you have several petals, one close to one another. And good thing with such a velocity kernel is that you can also disambiguate crossing trajectories, things that are looping with one another. That means that you can go from first order dynamics to second order dynamics. But going forward, when you build an adjacency matrix, what you usually do in graph theory is that you build the Laplacian. It's called a graph Laplacian, and for those of you who are familiar with machine learning, you may remember what is called spectral clustering. All of the theory of spectral clustering is based on the decomposition, eigenvalue decomposition, eigenvectors, eigenvalue decomposition of the graph Laplacian. So you do an eigendecomposition, and then usually what you do is that you study the eigenvalues. And it's been known for decades now that from graph theory that when the multiplicity of the eigenvalue 0 gives you the number of clusters. So if you have several times the eigenvalue 0 appearing in your decomposition, you know that you have that many clusters. Okay, that was known. But one thing that we thought we had discovered, but actually we found out that it had been discovered by a mathematician, a Russian mathematician, Fedor, a long time ago, is that if you study the eigenvectors of this matrix, what you find is that they have regularities. And you can actually extract eigenvectors. And the interesting part is that you can project your dynamics onto this eigenvector. So I'll make it very simple. If you study the eigenvalues, you discover that you have K clusters, for instance. Those K clusters are actually your K dynamics. So you have the answer. You know how many dynamics you have. But then when you look at the eigenvectors associated to those K eigenvalues with eigenvalue 0, then what you observe is that the entries of the eigenvectors are monotonic. And not only are they monotonic, but they are all following the same monotonicity. So that means that when you project onto those eigenvectors, your nonlinear systems appear linear. And for anybody who is in control, you say, hurry, because now you can control the system. It has become linear. It was nonlinear, it's linear. And not only is it linear, but you can separate. So I'm showing you an example here. We go back to either the Duffing oscillator that I've mentioned before, or a typical pendulum with friction. When you do this decomposition, you end up with two vector spaces that are orthogonal to each other. Why? Because you have the eigenvalues that you can decompose and the associated eigenvectors, so you can separate your dynamics, and in each of those subspaces, the red dynamics becomes linear, the blue dynamics becomes linear. You have identified the number of dynamics, and you have been able to separate them and to project them into subspace where they appear linear. After that, what you can do is learn a diffeomorphism to send you from the nonlinear, the original space, to the linear space and back, and stabilize your control system. We've just recently ported that for a variety of applications in robotics, typically doing highly nonlinear motions, such as following spirals in high dimension, and this is under review at the minute. Another aspect that we've looked at for years is how we can use this dynamical system for obstacle avoidance. In 2 dimension, it's trivial that if you have a vector field that brings you to an attractor, you can modulate this vector field and make sure that this vector field will still converge to the point, but not penetrate any obstacle. So this is an example here, and you can use this for navigating. When you try to do the same thing in joint space, as I show here, on the left-hand side, you recognize a robot arm with 2 joints in Cartesian space. But when you represent here in joint space the obstacle, which is only a circle, then this obstacle becomes highly non-convex. This is even worse if you want to avoid a person like this. So what we have developed was a way in which you can learn a representation of this free space and be able to navigate across this obstacle in highly nonlinear space. Here is an example of this application for being able to grab and manipulate object in hand and be able to not intersect the different fingers and the object. We also ported that for a humanoid robot. When you control a humanoid robot that has to pick up an object like this, the robot intersects itself very frequently, so the robot is an obstacle for itself. But you can learn a model of the free space, which is the obstacle, typically here with neural networks or with support vector machine also. And from this, be able to control a dynamics which will allow you to avoid obstacles in high dimension. I'll mention this work because I know that Mehdi Khorramshahi is here, and I was fortunate enough to have him in my group. He was doing his PhD and also as a postdoc. And he worked in this application of the dynamical system for being able to model force control in dynamical system. So you can model typically a massage motion, which is a set of circular motion with a translation, as we've seen before, as a couple of dynamical system, and then port this to control a robot. I'm just going to stop this for a second. So what does that give you? It gives you a set of dynamical system that brings you to here, for instance, a representation of the forearm, and on this forearm, you can oops, is it playing? Yeah. You can drive the system to go onto the arm and do a circular motion, and then also apply force by combining this as a magnitude amplification of the dynamical system along the normal trajectory. It was a very nice project funded at the time by Samsung, and this was ported for controlling here a robot that was actually doing a small massage on the forearm of a mannequin. Because of the natural stability and adaptation of the dynamical system, you can also adapt this to different translation and rotation of the mannequin, which is here tracked by a couple of sensors, and you have an ability to stabilize for this and to also adapt the motion and the force. More recently, we've been looking also at how to combine this with large language model. So it's been mentioned previously that LLM are doing wonders, obviously, but they also make mistakes. So we have used all the battery of dynamical system control with LLM. The LLM will give you a planning, and what we do is we combine this with the planner to be able to pick up a variety of objects. The planner often gives you wrong answers. So one thing that we've looked at is how we can query and improve the solutions that are given by the planner to ensure that we have a better estimate of the properties of the dynamical system and be able to control for the grasp and the position and the orientation. And we've ported that to be able to control also a robot's life. Here it was to clean up a table and to be able to do that with a real scene, which I will just show in a second, to do that live with the robots being able to pick up a variety of objects and trash basically all the objects that need to be trashed, or clean up the table by putting those that shouldn't be trashed at the right place. But as I said, I'm going to shift completely gears here because I would much prefer if we were to continue the discussion we had before I think all those discussions were more important than talking about technical details that we do in our work. So more recently, what we have been working for a while was to try to do more responsible robotics. So with the work on dynamical system control with obstacle avoidance, we have been deploying a robot. You will see it in a second, which is a wheelchair that can navigate in crowds. We've been using it in the city of Lausanne and deployed it and showed that it could safely avoid pedestrian, usually even in highly crowded crowds, as we see here for this is a marketplace during the day. We also did it at night. But the big question is, what if a collision arises? How can we prevent this, and how can we measure this? And we turn into assessing risk. And this is very different from what I presented this, but it was just to say that, I don't think our roboticists ignore that. And there are a couple of workshops regularly at ICRA, IROS, and also RAS is really looking into this to assess the risk for humans that robots are creating. And often those risks are underestimated. So one thing that we started looking at is what happens when first of all we design a robot shape that without taking into account the risk that it poses to a variety of pedestrians. And we looked at the variety of pedestrians that are perhaps more at risk than any other pedestrian. So you may be surprised to find out that most of the regulation in the EU are usually made for a pedestrian like this one, which is a tall man, about 1.80 m, not so much for children, not so much for women, and especially pregnant women. And why is it, what should we care about those people? Because of the height of the robot. When a robot hits a pedestrian, which is at a lower height, like here, or with a baby in the belly, and if you hit it at the wrong place, then you're hitting here the head, or you're hitting the belly. So this is an issue that needs to be taken into account in the design itself. So we started by first in simulation, conducting estimates of what is the most likely part of the body that you may hit when a robot is navigating with a pedestrian, assuming that the both of them are not really paying attention to each other, which is typically what will happen in a crowd. So you can do that easily in simulation. You can easily in simulation estimate the point of contact, the amount of force that will happen, and the directionality of the contact, which is so important. But simulation is simulation, and it's often different from the reality because the human body is also very complex, and it's very difficult to encompass a good representation of this. So we went to crash test facility that are nearby Lausanne, and we conducted crash tests using typically mannequin that they have. So this is a mannequin here. We put two mannequins, by the way, because when you have a wheelchair, the issue is for the pedestrians, the bystanders, but there are also issues for the person on the wheelchair. So those two mannequins are standard mannequins that you find in crash tests for automobile. You can measure the interaction force at various points in almost all the joints of both robots, treat them as robots. And so we conducted a systematic assessment of what happens if the robot here is hitting the pedestrian. But we also did it with a child mannequin. And that was much more complex because, as I mentioned, nobody really cares about this category. So we really had to look for a child mannequin. And when we found that last one, it had no force torque sensors on it. As surprising as this can be. So it took us a while to just engineer and put enough force torque sensor to be able to measure what happened. We did also systematic assessments to see what is the effect of hitting it at different places. And I know those videos are not nice to see, but luckily they are with mannequin at this stage. To assess what is the effect of hitting the head versus hitting the chest. We systematically assessed also what happens when you apply different speed regulation. So first, speed regulation vary across countries. They vary widely. Really, as you can see, they go from 1 meter per second to 2 meter depending on the region. These are sample videos of contrasting hitting at the head or hitting at the chest with this different speed. We estimate, so we drive with this, we tested all speed limits. We did not go beyond the speed limit, but we assumed that we were driving at the speed limit and that the child or the adult was walking towards the object. That means that you exceed always the speed limit, right? Because you have two velocities that are opposite to each other, so they add up. And we looked then at, so we estimated, based on the force data that we measured, whether we were exceeding potentially the risk of injury according to standards that exist now. Yes, so sadly, yes, you do exceed that very rapidly. So the probability of skull fracture and serious injury arise already at 1.4 meters per second for the child. And even for the adult, they do arise also quite likely. But, and be careful here, this is not for adults like you and me. These are for adults who don't have a good balance. Who are those adults? They're elderly. When you hit an elderly, in fact, the issue is usually that the elderly falls. And this is what we're seeing with our mannequin. Our mannequin is actually not trying to rebalance itself because it's not a robot. And this is what happens when you fall, you have secondary injury. So you're still within speed limit, but the issues are high. And the issues have to do also with the design of a robot, basically the mass, the inertia, because this is not just about speed. We all know the speed limit is ridiculous. In fact, it's acceleration, it's energy. But try to convince, lawmakers that it's about energy. I'm also, in my spare time, I sit in the parliament in Canton Vaud, and whenever I try to talk to them about watt or energy, I'm talking Chinese, right? I mean, I'm sorry, I'm not to take it wrong way, but they just don't get it. So what we can do as engineer is think about this. And if we look at all the robots that are currently deployed in pedestrian area, they all exceed largely what is deemed as acceptable if there are some of these injuries. But we could lower the weight. We could lower the weight by design. It's not too difficult. We could also lower the height of the robot. So this is my plea, is we as engineer, and it's really a low-hanging fruit, we can make a difference. We can really engineer in such a way that we limit the speed beyond the regulation on design, by design, when we control for this robot. We could also reduce the robot's weight, or let's say mass, the way that we design it. We could also provide enough sensors. Often, and I see it also for autonomous cars, the number of sensors that are placed are small in comparison to the price of the car, and I think we could put more easily. And also, if collision is unavoidable, and collision will be unavoidable, it's like wars, they are unfortunately unavoidable, then we need also to think about that, and we need to think about the design of things that can absorb the energy. It's been done for robotic arm. There is a lot of work on this, beautiful work, typically by Sami Haddadin. Much less is done at the minute for autonomous vehicles. We need to have autonomous vehicles that can absorb actively some of the energy and the impact. And I know that Madis has been working a lot on this also in his group. And finally, it's been mentioned earlier on that yes, there are many, many more laws that have been brought forward recently. I don't think that standards are following at the same speed, unless I'm mistaken, and I will be happy to discuss this more. My impression is that we need also to adapt standards much more rapidly and to adapt the risk analysis. So this is a plea, and I'll love to have a conversation on this. With that, I really want to thank all the people in the lab who worked on that. For the last part that I discussed, it was really the work of Pericles Arlini and Diego Paich on ethics and safety, and as I mentioned, all the different people who worked on the control system. I want to thank also Ran, who gave us the opportunity to write an MIT Press book that this summarized now the more technical part that I've presented before. The book is available for purchase. We also created a class based on that. So we have lots of examples of the video, the lectures. You can get all the codes on our website, the slides, the videos, and also MATLAB codes. So if you're interested in the dynamical system that I've shown, then you can get access to that. And I'll be happy to answer your question. Thank you for your attention.
so we have some time for questions. No? Ah, there are some over there.
Yes, thank you very much for your very nice talk on these two parts. My question will relate more to the first part. You talk about the importance of having physical laws and to use them and to predict them and not to use only data. But my question is that how do you see the merge between the two worlds of physics and data science, and what is a good blend of the two worlds? Should you have a little bit of data science and lots of physics, or a little bit of physics and lots of data science and data-driven methods? So yes, if you can comment on these aspects and what, in your view, will be the good mix of the two. It's not a very easy question, but.
Yeah, thank you very much for the question. It's not an easy question, because what is a lot and what is little? Is it the amount of time that you spend solving a problem? And so yes, or is it the amount that you put then in a computer? If, for instance, for the obstacle avoidance in high dimension, we have a lot of data to be able to represent the free space, the obstacle in joint space. Huge amount of data, neural network trained for hours, etc. So it's a lot, if you want, in terms of data and the training, but it was a lot of thinking to make sure that the representation we have provide guarantees of impenetrability, that you are sure that you have some guarantees that you can exceed also some local minima, etc. So it's a balance between the two. The best I've found over the years is to have people who are skilled in both domains. In robotics, at the minute, it's a mix. We have people coming with more computer science background, let's say, and people with a more control background, some from physics or applied math, and some from electrical engineering or mechanical engineering. And it's good. And I think it's good to have these two crowds. The best is to team them up. I've seen this in my group often, to bring them together. When people come with a background like computer science and try to go into control, or conversely, it takes a long time and it's not that trivial. But when they work with one another, this is really when you get wonder. So at least, but this is very selfish, this was the best, the most practical way. Yeah. Perhaps what we are lacking, at least in my university, are joint degrees. We still have traditionally computer science degree, or traditionally mechanical engineering degree, not so much joint degree where we bring people up to speed with both type of backgrounds. But maybe it's just particular to EPFL, I don't know.
Hello, thank you for the nice talk. So I'm here.
Oh yeah, thank you. There's a terrible light here.
So it's a bit the same kind of question, but maybe more specific. So in my sense, robot learning might be differentiated from other kind of AI learning. One of the key differences would be actions. So what's your point of view on that? Is it something specific in robotics, the representation of actions? Or the fact of doing actions and not only decisions. What can robotics bring that, let's say, current AI techniques don't do, especially through your experience with LLMs also? What do you think can be the limitations of the current LLMs towards embodied and grounded actions?
Yeah, thanks a lot for the question. And I know you work in a similar domain and you're already doing symbol grounding to a large extent. So today, clearly, the need that we have for machine learning and robotics is distinct from what is developed purely in machine learning. There is a wish to go for large data sets. And there is a crowd in robotics that is trying to get huge, large number of data points. I don't think this is the best way to address this problem. If I take Robin's example, which are sublime, you go to disaster area. I don't think you're gonna, well, probably with climate change, we're gonna see more and more examples of those, sadly, but I don't think you're gonna get that many examples to be able to train your robot from this. So you're gonna have to act in a world that is, to a large extent, unpredictable or unseen before. And what is particular to robotics is the fact that when you act, it has immediate consequences. Of course, it does have consequences for generative AI when you have a dialogue system, but the consequence of a robot that is driving on the road and suddenly driving on the pedestrian lane is catastrophic in many different ways. It can really kill people unwantingly. I mean, we're not even in a war environment, right? And so we, and people will overreact to that. So it's complex. We need, in my view, we need to work to develop more algorithms that allow incremental learning with guarantees, formal guarantees. And that's not easy because that means that you need to decide when you destroy previous data and when you add new data and what is the effect on the model. So you need to have a way of, really have a readout of the model and the stability of the system in the action. The action of the robots depends so much we know on the robot. This is all about transferability. One robot is different from another robot. The embodiment is distinct, but even the same robot is not the same as you keep using it because there are so many other effects. At least just in my group, when we use the fantastic KUKA robot, after a few hours of running the robot, the behavior is not exactly the same. It heats up, and sometimes it will just not react at the same speed. Joint friction may vary. The sensors also may vary. So there are lots of aspects that have to do also with signal-to-noise ratio, which I believe is very high in our system, which are looked at in automation. So we have needs in robotics for making sure that the action of the robot are controllable and learnable, that are distinct from traditional machine learning, and needs more work in this area that's specific to robotics. That's my stake to that. I would love to hear from other people what they think. Actually, if you have time, we could make it an open discussion.
Feel free if you want to comment or.
One thing we could take from the machine learning community is that they have a mic which is a ball and they throw at the crowd.
Thanks for your talk. And to follow up on this, what is the role of interactive robot learning? Like, how can we make use of this to have an iterative learning process where you have the human or you have a system that is trying to learn new things guided?
Sure. So there are different ways in which the human can guide the learning. One is obviously by demonstration. You do a demonstration with all the problem that we know, which is that your body is different from the robot body, so you have the so-called correspondence problem. The second is to give guidance, which is reinforcement learning, saying it's good or bad, and just at the end, the credit assignment problem, and it's been looked at. And then you have the last one, which is active learning, which is probably the most promising one, where you start having a dialogue with a robot. And in that sense, I'm hoping that with LLM also this type of interaction will be easier to do for the robot to possibly assess and tell to a naive human, look, I really don't know anything about this part. Can you please teach me? We had done that for dynamical system a long time ago, where when you learn your dynamical system with very few data points, there are areas that are not covered by your data points. And so you are going to make inference. You will assume that the dynamics resemble the one that you have seen in this region of the state space with some formal guarantee. But chances are that it's not the case. So then we wanted a robot to query the human. The problem is that most humans have no idea how the dynamical system is represented in the robot. So it was very difficult to convey that to the human. We tried different ways in which you could display the dynamical system, but as soon as you are more in three dimension, it's invisible. So it would be nice if there were ways in which this could be conveyed with language. I don't know exactly how that could happen, how that could be done, but I have good hope that this could be a nice area of improvement, hopefully, of the interaction with humans.
I had a question related to your second part of the talk and wanted to draw links with a presentation by Ronald earlier. So as you saw, different users have different vulnerabilities. So, and that raises the question of a trolley dilemma, you know, if you cannot avoid an accident, should you target the tall guy or the young kid? And in your kind of robots, you could implement that, maybe. You could imagine implementing that at least, and making a decision on how to, who is the recipient of the accident. Do you think there could be a place for this in ISO regulation? Do you think it's doable to do that, or do you see as impossible? And just
Actually,
to add,
I mean, I totally agree. I mean, I thought about it. So typically, when the robot is about to crash into either the kid or the elderly, or let's say me, the robot should choose me, right? Or not, it depends. Or you will say, okay, choose the elderly because the lifespan is shorter. And it's funny because when we started discussing this, it was just a year later, COVID started, and people were actually asking themselves the same question. In my country, in Switzerland, I'm sure in France as well, they literally drafted guidelines saying, if you have to choose, you let the elderly die. And so when it comes to it, I think the society is almost ready to make that decision. It's a difficult one. I don't know. But at least from one decision we could take, as opposed to decide which one gets killed, which is really the ultimate catastrophic, outcome, is least damage. Obviously, if you're hitting the child and you know that the probability of a severe, head trauma is higher than it is for hitting another of the pedestrian, perhaps you could put that into the controller.
seems reasonable.
It's difficult.
Okay, one last question.
Many thanks for this nice presentation. Yeah, very, very beautiful, mixed between several areas, and I saw very, very nice results in all cases. So my question is related to the risk assessment. When you propose the techniques to avoid obstacle, you told us that you have to reduce the velocity to avoid obstacle, or when the risk is high, you reduce the velocity. What about the shifting? So how you can plan other paths, not straight path. And the second question is related to the your metrics to characterize the risk. I think I don't saw element around that. Thanks a lot.
Yeah, sure. So taking another path and avoiding obstacle is the first thing one should do, obviously. But when you navigate in a dense crowd, there are often no free path, and it's often when collision arise because they're unavoidable. The question is, or when the risk, well, let's say the probability that a collision will be unavoidable arises as an effect of having a very dense crowd around you, then my recommendation would be slow down. Don't go at the speed limit. It seems obvious, yet not everybody will do that, right? Because they will say, I'm still driving at the speed limit. So it's like I sometimes have the impression to just say things that are absolutely obvious, like la police, essentially, saying the things that. But when you look at the way that people drive, and you know that in France, and it's the same in Switzerland, especially in Europe, it's a little bit nicer, I find, in the US, but they tend really to take the speed limit not as a speed limit, as the limit at which you should be driving, which is already something different, right? You see 50 kilometers, and then you go and you drive at 50 kilometers. No, this is an upper bound. It's not a target. You shouldn't be at 50 plus minus 5 kilometers. You should be under 50 kilometers. But that's not the way that people address that. If we build that, if it's normal for us when we build control systems, software for robots, that we take into account things that we know well as engineers, an estimation of risk that we can do based on an analysis of the surrounding, an estimation of the risk based on the amount of energy that we know from the mechanic of the system, how slow it is at braking, the mass of the robot plus the pedestrian on the robot, which is much heavier, like typically in the robot that we have here. The total mass is 100 kilo, 120 kilos, not because the pedestrian is heavy, but it's pedestrian plus the robot. All of this, if we put that in the system, if we find it's normal, whenever we have someone giving a talk, that it's normal that a person documents the safety that the student, you're a graduate student, you build a new software for your robot, and then not only do you document the performance of your system, but you end up your paper by saying, and by the way, in addition, I also already built in those safety mechanisms. I know how to program that, so I do this. Why not? It's a low-hanging fruit. So I think we should do it.